feels, or at least it felt then, like different communities were prescribing very different things about how we should fundamentally think about model design. If you look at econometrics, for instance, there's a strong emphasis on parsimony and building models with a very small number of parameters that are interpretable, et cetera. Whereas in machine learning at the time, and I would say still now, there's often an emphasis on building huge models, kind of as big as a house, with a lot of flexibility. And really, it seems like the goal in building a new model was greater expressive power. And so a lot of my PhD at the beginning was spent trying to reconcile these two perspectives in a sense. How could it be both, that we want parsimony and simple models, yet we want really highly flexible models that are very expressive? And part of the resolution was that, as I came to see it, that generalization was at least a two-dimensional concept. It wasn't just to do with flexibility. It really had a lot to do with the combination of model flexibility and inductive biases, which are broadly the assumptions that we make that enable the model to have preferences for certain types of solutions a priori over others. And that's something we'll be discussing throughout the talk. And that the talk will have 4 different parts, and we'll go through some of the details of each of these. Some of the especially new content that will be in the talk will relate to an approach to representation learning that doesn't explicitly invoke neural nets, but it still has a deep learning flavor. I think as deep learning matures, we're starting to understand that it isn't just about neural networks. It's also about deep graphical models, about hierarchical structure, about a lot of the high-level ideas that sort of have provided deep neural networks with good inductive biases for generalization on a number of different problems. And so we'll touch on functional kernel learning. We'll also talk about other types of kernel learning, which are in a way how you do representation learning with Gaussian processes and other types of kernel machines. And we'll also talk about optimization procedures, which have been inspired by Bayesian deep learning in a sense. In many cases, it can be computationally burdensome to carry around a lot of models that we might want to be using if we're deploying a Bayesian neural network. And so one interesting research question is whether we could represent something like what we would get through a Bayesian model average with just a single model. And one way we can do that is through optimization. 1 second. Okay. And so in that context, we'll also be discussing loss landscapes and how we can try to understand the geometric properties of the objectives that we normally use to train neural networks in order to provide both better Bayesian approximations, but also just better solutions if we're ultimately going to be doing something like optimization, as well as better exploration of these loss surfaces if we're trying to use procedures, especially like stochastic gradient Markov chain Monte Carlo. And in a way, I would say, one distinguishing property of Bayesian procedures is we're really not trying to bet everything on a single solution. We're trying to consider all solutions and then take a posterior weighted model average. And that means that exploration, in a sense, is going to be particularly crucial. From the perspective of optimization, we just want to find the solution with the lowest loss. There are other properties that can affect generalization, like the flatness of the solution, et cetera. But fundamentally, the optimization problem is set up to find the lowest loss solution. Whereas from a Bayesian perspective, we want to move all over the surface. And so when we're thinking about stochastic gradient MCMC algorithms, we'll really care about things like learning rate schedules beyond just using them to try to find the low loss solution efficiently. Okay, so to start, we have this comic from XKCD where we have 2 people talking. First one says, this neutrino detector measures whether the sun has gone nova. Next person says, then it rolls 2 dice. If they both come up 6, it lies to us. Otherwise, it tells the truth. First person says, let's try. Detector, has the sun gone nova? We hear the dice rolling. And then it says, yes. And then the figure splits, where we have the frequentist statistician saying the probability of this result happening by chance is 1/36, 1/6 squared, which is less than 0.05. So I conclude that the sun has exploded with statistical significance. And then the Bayesian says, bet you $50. It hasn't. So this cartoon isn't a perfect description of the 2 camps in a sense, but You might say, well, if your reaction to this cartoon could depend also on what field you're coming from. If you're a game theorist, you probably would say, why just $50? Why not everything? Because if the sun has exploded, you have nothing more to lose. So in this sense, the Bayesian is also being a bit foolish. If you'd like to sort of see a detailed calculation of the posterior odds of these different hypotheses, which is something that Bayesian would want to compute, you can try Googling this, and people have gone into quite a bit of depth in trying to come up with a reasonable sort of ratio of odds, given that the detector is telling us that, yes, the sun has gone nova. The basic intuition, though, is that we've probably played a number of board games and rolled 2 6s. This isn't a particularly unusual occurrence. The sun exploding would be a priori an extraordinarily unlikely occurrence. And so that's really going to dominate when we compute the posterior odds of these two hypotheses. And there are a number of fun examples in David Mackay's information theory textbook where he computes ratios of posterior odds for various different hypotheses, and also argues that from the Bayesian perspective, if we're doing model selection, the marginal likelihood, or the Bayesian evidence, is going to automatically favor a model of low complexity as long as it's consistent with our observations. So there's this fun example where we have basically a tree and what appears to be a block behind the tree. And then the question is posed, well, maybe if we had X-ray vision, we would see that it's not really one block, it's 2 blocks or 10 blocks or 100,000 blocks. But if we didn't have X-ray vision and you were just to ask someone how many blocks are behind the tree, they would almost certainly say with pretty high confidence 1 block, and they might try to rationalize that decision by saying it might be a remarkable coincidence for there to be 2 blocks of exactly the same height and color behind the tree, for instance. And so this is sort of an Occam's razor property that's actually automatically encoded in Bayesian inference. And we'll see some examples of that throughout the various parts of this tutorial. And so even if we don't have a prior that says that these 2 hypotheses are equally likely, we can have a posterior and a marginal likelihood, which will be favoring the simplest explanation that's consistent with our observations. And from an information theory perspective, this is also connected with what are called minimum description length principles, where we want to basically provide the most compressed representation of our data, and that will tend to capture a lot of regularities that will provide good generalization. Okay, so I'll start with a pattern recognition problem. You may have seen me ask this before if you've seen some of our recent talks, but it's a nice way of tying everything together. So we have our airline passenger numbers recorded monthly, and we'd like to make predictions, say, into the future up to 1961, and we'll consider 3 different modeling choices. Choice 1, a linear function. Choice 2, a cubic polynomial. And choice 3, a 10,000th order polynomial. So at this point, I'd like to pause and take a vote, and I think the summer school has a poll set up that you can answer, so that you can say which choice you might make for this particular problem. So I'm seeing a lot of 1s and 2s in the chat, no 3s. And 3 is precisely what I'm going to be arguing we should be doing throughout the tutorial. And in fact, I might find 3 unsatisfactory because it's not sufficiently flexible. So in practice, though many of us would indeed go with choices 1 or 2 for fear of overfitting, we know that there's some setting of parameters in choice 3, the WJs, which will provide a better description of reality than could possibly be managed by either choices 1 or 2, which are just special cases of choice 3. And if we had a good way of learning those coefficients, then we should expect better performance. And a good modeling procedure should try to capture our honest beliefs. And our honest beliefs are typically that the real world is a complicated place. Also, in practice, many of us, without really thinking about it too actively, are already using models with many more parameters than data points. We often use neural networks, big residual nets, for instance, that have tens of millions of parameters on problems like CFAR 10, which have 50,000 data points, and find that we get very good generalization. We're also seeing empirical results like double descent that suggest that we can get very good performance with a large number of parameters. And as we'll see in the last part of the talk, those results are entirely consistent with a Bayesian perspective, where we really don't want to be treating parameter counting as a proxy for complexity. And instead, we want to be using flexible models that also have reasonably good inductive biases. And in the next part of the talk, which we'll actually be doing today, we'll be considering models with an infinite number of parameters that are, in a sense, like if we could use an infinite order polynomial, and finding that we can get very good generalization on problems with even a very small number of data points. So throughout this tutorial, we'll really be arguing to build models that are as flexible as possible. And to start understanding the motivation for such models, it's helpful to be thinking from what's called the function-space perspective, where we're not directly sort of parameter counting and considering the parameters, but rather considering how those parameters come together with a functional form of a model to induce a distribution over functions. So here we have choice one, the linear function, w0 plus w1 x, and we just put a standard normal distribution over these parameters. And this will induce a distribution over functions with different slopes and intercepts. And we can visualize this distribution by sampling from our prior over w0 and w1. We get different values, and then we just draw the corresponding straight line. The gray shade here shows our 95% credible set, which contains 95% of these functions. And the solid blue line shows our expectation of this distribution over functions. In this figure here, we have a conceptualization of all possible data sets on the horizontal axis, and the marginal likelihood, or the evidence that I was just referring to a few minutes ago, on the vertical axis, which is the probability that we would generate a data set if we were to randomly sample from the parameters of our model. And so in blue, we have a conceptualization of that linear model that we were just considering. No matter which w0s and w1s we sample from this distribution over the parameters, we won't be able to generate many different data sets, just straight lines with different slopes and intercepts. And because this marginal likelihood is a proper normalizable probability density, it's going to have to give a lot of mass to those data sets because it's not representing any other data set. On the other hand, we can consider a different type of model. For instance, maybe a really huge multi-layer perceptron and a broad distribution over the parameters. And such a model might be able to generate quite a wide range of data sets, but it could distribute its support over those data sets very thinly, such that it's not strongly preferring many data sets over many others. And so this type of model will be said to have not very good inductive biases, which describe which solutions we think are a priori likely. We can consider a third type of model, like a convolutional neural net, which is in fact very flexible, but it also has very strong inductive biases encoded through properties like translation equivariance, this idea that if we translate an image, its class label should be unchanged. And these inductive biases are very important for generalization on a lot of high-dimensional natural signals. And in fact, there are other types of symmetries that we might also want to capture. So this green model, in a sense, manages to do both. It manages to both be flexible, but at the same time have good inductive biases that'll also be important for good generalization performance. And throughout this tutorial, I'll argue that these are really the properties that we want. Large support, being able to represent a lot of different solutions a priori, because that's just representing our honest beliefs about the world, that it's a complicated place and we want to cast a wide net. At the same time, we don't necessarily think all of those solutions are likely. They might just be plausible, not probable. And so we can reflect that with inductive biases. And we should really be careful not to conflate flexibility, which I might call the support in this instance, with complexity. We can have really flexible models, like the models I briefly alluded to a few slides ago, with infinitely many parameters that, in a sense, are also quite simple. They have fairly simple inductive biases, which enable great generalization on problems with even a small number of points. And so in this figure on this slide, we have in the first panel what we observed on the last slide, plus 3 additional panels, which describe what happens as each of these models is exposed to a given data set. So the green model has large support and also reasonably good inductive biases, so that when it observes data, it's able to efficiently contract around a good description of reality. The second model in blue has very limited support, and it actually can't describe anything that's remotely like the ground truth description of our observations. And though it is quickly constrained by the data, it in a sense is erroneously constrained, and it just collapses down onto a not very good solution. And then in this third model, we've cast a big net so that we can capture the truth corresponding to some setting of our parameters, but we have our inductive biases very thinly spread over all sorts of different solutions. So the model isn't able to efficiently adapt with new information. And so it doesn't really contract very effectively around a good solution and still doesn't provide very good performance. So in this tutorial, we'll be thinking largely from a Bayesian perspective. Even if not everything we're doing is explicitly Bayesian, it'll be motivated by this perspective. And I would argue that the key distinguishing property of a Bayesian approach is what's called marginalization instead of optimization. So that is, consider all possible settings of parameters rather than just bet everything on a single setting of parameters, which is what we do typically when we're performing optimization. And so in this figure here, we can see some data points, and we can in fact see many different functions that might be consistent with those data points, and in a sense could be reasonable. If I said, well, is it this solid blue function that we believe, or one of these other curves? It would probably be hard to tell. And probability theory just says that we should combine all these solutions together, and it gives us the sum and product rules as a good mechanism for doing that. So I've long been interested in Bayesian machine learning. I became quite interested in Bayesian deep learning, ironically, after listening to a talk about optimization, which could be ironic given what I just said, in that Bayesian methods could potentially be described as trying to avoid optimization at all costs. The argument that was being made in this talk was that mini-batch SGD would provide solutions which would typically generalize better than full-batch gradient methods, because they would converge to flatter regions of the loss surfaces that we're using to train these models. For example, mean squared error or cross entropy if we're doing classification. In this figure, we have the loss in black. On the horizontal axis, we have a conceptualization of parameters. The testing loss is in dashed red. And we can see that a flat solution has pretty good testing loss, but a sharp solution has pretty bad testing loss after there's this horizontal shift between training and test loss surfaces. And we would typically expect this shift even if the train and test points come from exactly the same distribution, if we're evaluating the loss functions on some finite set of points. You could imagine, for instance, if you added or removed samples from your training set, you would really hope actually that you would update your parameters. So unless the model is entirely determined by that data set, we would expect a shift. And the shape of the loss surfaces are relatively similar, because we still believe that the training loss is not a horrible proxy for generalization. Now, for this argument to really mean something, the different parameters within this flat region would have to give rise to different functions. So, for example, when we were considering that linear function, the different W0s and W1s gave rise to quite different types of solutions. And otherwise, the flatness might not mean so much. We could achieve it trivially, for example, through reparametrization. So if that's the case, then this idea of doing Bayesian marginalization, also known as a Bayesian model average, is particularly compelling, because it means that there's going to be all these different parameter settings that actually give rise to different functions, which are all compelling explanations for the data. So in a sense, we're actually getting quite a rich ensemble of diverse models. And that's going to provide a very different answer than if we just bet everything on a single model. So although it has taken some time for Bayesian methods to be broadly deployed in deep learning, where they're perhaps more standard when we're using models like logistic regression right now, in fact, the benefits could be the most significant on these types of problems, where our loss surface is telling us, actually, there are a lot of good solutions to this problem. And the result that we'll get by basically doing this marginalization procedure will then be quite different. And so there are many reasons to be excited about Bayesian methods in deep learning. As we've just discussed, neural nets can represent many complementary explanations for the data. We can get better uncertainty representation through representing what's called epistemic uncertainty, which is, for instance, uncertainty over our parameters, distributions over parameters. We'll talk about that in more detail later, which is crucial for decision making. If we want to make a decision, it's helpful not just to have a point prediction, but to have a whole distribution over what the predictions could be and how probable they are a posteriori. And you might argue that if your method is inconceivably going to have any effect on decision making, then it might not really have, a practical impact. So these methods are very important, I think, for deploying deep learning in the real world. But a perhaps less well understood benefit also is just better accuracy, better point predictions. If we are combining all these great complementary models together, we'll often see much better accuracy in our predictions. And this is also something that's starting to be realized. It has been very successful in the past. So as you may know, neural networks have been around for quite a while, and their popularity has come and gone in waves. And in the second wave of neural nets in the mid-90s, Radford Neal showed by developing Hamiltonian Monte Carlo approaches to inference that Bayesian neural nets could actually win all sorts of different competitions and solve a lot of interesting problems. His approaches wouldn't scale to modern architectures, but those results do tell us that there's some treasure buried in the direction of Bayesian deep learning, and we just need to build the right tools to extract that treasure as a community. And as we've already started to discuss, and as we'll discuss much further, neural nets become much less mysterious when viewed through the lens of probability theory and Bayesian inference. Things like double descent become actually quite natural. The idea of having many more parameters than data points is really not a problem if we're not treating parameter counting as a proxy for complexity and we're thinking in function space. The idea that neural nets can fit randomly labeled images also isn't problematic from this perspective, where we want our models to be flexible, but we also need them. Why not? Well, these methods can be computationally intractable. They can involve many different moving parts, but they don't really have to. And there's been a lot of great empirical progress in the last year where Bayesian neural nets have been providing often better practical performance than classical training without a lot of significant overhead. And we'll be discussing a number of these methods in part 3. So here we have a brief outline. In this first part, we'll be discussing foundations. We'll be doing an overview of some of the other parts of the tutorial. We'll be really emphasizing the importance of model averaging in deep learning in particular. We'll be talking about epistemic uncertainty, and we'll be exemplifying a lot of these ideas with examples. In the next part, we'll be considering largely a function space perspective of machine learning, where we talk about Gaussian processes, infinite neural net limits, how training a deep neural net is like kernel learning. We'll also discuss functional kernel learning and Bayesian nonparametric deep learning. And in part 3, we'll be considering a number of practical methods for Bayesian deep learning. And we'll also include in this discussion Bayesian generative models, which I think are a very exciting and up and coming sort of area of research for Bayesian methods in deep learning. And in the last part, we'll be talking about model construction and generalization, including deep ensembles, their connection with Bayesian marginalization, how we can build on those connections for the multi-swag procedure, tempering in relation to some work about what are called cold posteriors recently, prior specification, rethinking generalization, double descent, width depth trade-offs, and trying to view many problems around generalization and deep learning from a Bayesian perspective. Okay, so we'll start out from scratch, just forgetting everything we know about statistics and machine learning briefly. And we'll use this example to introduce a lot of notation that we'll use throughout the talk, and also to start really reasoning about model construction and generalization from first principles. And so imagine we'll have a training set of n targets. These could be like our airline passenger numbers, indexed by our inputs, the x's. So in this case, the x's could be different times. And our goal is to predict our outputs y at some test inputs x star. for example, if we're given airline passenger numbers that we observe here, we might be interested in predicting the number of passengers in 1961. And so I'd like you to pause just for a minute and just kind of relying on high school math and nothing you've learned since then, think about what approach you might try on this particular problem. So if it were me in high school, I would start by thinking about the functional forms that I'm familiar with, like sines, cosines, exponentials, polynomials, etc. I would look at the data pretty carefully and try to create some combination of those elementary functions to describe the patterns that I see. The function that I get as a result would have some free parameters, and I would try to learn those parameters by specifying some error measure. For example, the difference between the squared, the square difference between the outputs of my function and the actual points that I observe expressed here in this equation. And then I would minimize this with respect to those parameters somehow. However, many of the design decisions there would be pretty arbitrary. For example, it's unclear that I should use squared error versus absolute error or some other type of error measure to train this model. We could alternatively follow a probabilistic approach where we assume that the points are drawn from some latent noise-free function, f of xw, which would be like my functional form that I was considering, plus, for instance, additive ID Gaussian noise with variance sigma squared. And we can use that observation model to create what's called a likelihood, the probability density for the data that we observe. And then we could maximize that likelihood with respect to our parameters, in this case, the parameters w of our functional form and sigma squared, our noise variance. However, if we take logs, for example, of this particular likelihood, we can see that the objective that we get will give us the same answer as just choosing squared distance. And so you might wonder, well, what's the point of doing all of this if we're just getting the same answer in this case? And there are a couple of reasons why this perspective here is preferable. So first of all, it's much easier and more intuitive to think about, for example, whether our data has Gaussian noise than whether we should use a squared error function just out of the blue. And in fact, if we make other design decisions, like we use heavy-tailed noise, like a little Laplace distribution, maybe we think they're outliers, then we'll recover different types of error functions, like the absolute error function. Also, if we believe our model to some extent, we can get an estimate of the noise variance in the data, which is great. And so we can basically use this type of approach to interpret design decisions which otherwise would have been kind of ad hoc, and to come up with new design decisions which might be compelling for a given problem. However, remembering what we know about statistics, you're probably aware that either of those approaches can be prone to overfitting. And in fact, that's probably why most people went with option 1 or 2 in that beginning question. We can try to combat overfitting by doing what's called regularization, where we introduce some kind of complexity penalty, which says that we don't want to use very large weights. And we can calibrate the magnitude of that penalty with a hyperparameter like lambda here, which can be set, for example, through cross-validation. We could also get some kind of interpretation of this penalty by considering a log posterior, which is equal to a log likelihood plus a log prior, and the log prior would be, in this case, a bit like regularization. Not Bayesian, because still we're doing optimization, betting everything on one hypothesis. But this is all a bit ad hoc again. It's pretty unclear how we should be penalizing complexity. Whether we want large weights or small weights would entirely depend on the parameterization of the function that we're using. And if we had many such penalties, it could get very expensive to try to learn these lambda-like parameters. We'd end up with a cursive dimensionality. And we'd also have to make all sorts of design decisions in doing cross-validation, like which validation sets we want to use, et cetera. And there'd be all sorts of trade-offs. We could alternatively follow a Bayesian procedure. There's not much you really need to know to deploy a Bayesian procedure in your own work. We have Bayes' rule, which is often expressed as a posterior being proportional to a likelihood times a prior. The normalization constant here, the marginal likelihood, is what we were considering on that slide where we had all possible data sets on one axis, and the marginal likelihood on the vertical axis. We have the sum rule here, which says that the marginal distribution over x is equal to the sum of the joint distribution over x and y, summing over y. We also have the product rule. The joint distribution over x and y is equal to the product of the conditional distribution p of x given y times p of y, or the conditional distribution of p of y given x times p of x, and we can actually derive Bayes' rule from the product rule. And so there's not a lot you need to remember to use a Bayesian approach in your own work. So ultimately, what we're really trying to compute in many cases is this marginal predictive distribution. So y given the data, bold y, but not y given parameters. And the sum and product rules just tell us that that's the integral of y given the parameters times the posterior over the parameters given the data integrating with respect to the parameters. So this is called marginalization because the parameters w appear on the right-hand side of this equation, but not the left-hand side. We've marginalized out w. This is also a Bayesian model average. So in words, what it's saying is don't just use a single setting of parameters, use all possible settings of parameters weighted by their posterior probabilities. And so this isn't a controversial expression. It's just a direct consequence of the sum and product rules of probability. And it represents what's called epistemic uncertainty over which function f of xw fits the data. So epistemic uncertainty is reducible uncertainty with more information versus aleatoric uncertainty, which is irreducible, which in this context, this running example would be like the noise in the data. And so there are many different solutions that could be consistent, and we should represent them. We don't have complete certainty over which function corresponding to which setting of parameters is the right solution given a limited amount of information. And this will help us sidestep issues associated with overfitting, because we're not betting everything on one model. We're not really doing any fitting. We're just following the rules of probability and trying to honestly represent our beliefs in the modeling procedure. We can also view classical training from this perspective as a special case of Bayesian inference, where we use an approximate posterior, which is equal to a delta function, centered on the maximum likelihood or regularized maximum likelihood, the map setting of parameters. When we substitute in this expression for Q into our expression for P of W given data in equation 11, we see that we'll actually just recover the predictive distribution that we get when we do maximum likelihood. We'll get P of Y given those maximum likelihood setting of parameters. And so we can see here a couple important observations. One is that even if we have an approximate posterior, which is not a great description of the true posterior, it could still be a lot better than just using an approximate posterior that's a delta function, which could be even a much worse description. And so, for example, if we use something like a Gaussian approximate posterior in deep learning, it won't capture the multimodality that we typically see in these objectives, and it'll miss a lot of important structure that we, in principle, do want to capture. But it could still be providing us with a much better approximation to this integral than what we would be getting with just a delta function. And so we don't need to perfectly approximate this integral in order to at least provide great improvements over what everyone else is already doing when they're doing regularized classical training. We can also see that this Bayesian approach is going to be most different from a classical approach when the posterior is not very concentrated around a single setting of parameters, or when the conditional predictive distribution, P of Y given W, is changing quite a lot for different settings of W where the posterior has mass. And so this is exactly going to be the case with neural networks. And this is when we're most going to want to deploy a Bayesian approach. So neural nets can represent many complementary explanations corresponding to different settings of their parameters W, and we know that these loss surfaces are crazy, and we'll actually see some fun visualizations of these loss surfaces later on. There's an important distinction between Bayesian model averaging and some types of model combination or ensembling. So the fundamental assumption in a Bayesian model average is that a single setting of parameters corresponding to a single hypothesis is the correct setting of parameters. And some approaches to model combination assume that we actually want to use a combination model as a ground truth description of reality. And so the model average here, even though it is combining together different hypotheses, it's because given limited information, we don't know which hypothesis is correct, but we believe that one of the hypotheses is correct. And so this will typically be safe if we actually have a pretty broad hypothesis space, which contains all sorts of different solutions to a given problem. And if we have good inductive biases, then the posterior will start to collapse around a good description of reality. If the actual ground truth is a combination of models, then we could see the model average actually performing worse as we get more data. So there's a fun tech report on this called Bayesian model averaging is not model combination. So we'll now consider two different examples. So I'd like you to suppose that we're flipping a biased coin with a probability lambda of landing tails. And I'd like you to consider these three questions. First, one, what is the likelihood of a set of data? So we've done n flips, and we've recorded which ones are tails and which ones are heads. What is the maximum likelihood solution for lambda? And three, suppose the first flip is tails. What is the probability that the next flip will be a tails using maximum likelihood? And you might want to substitute in some concrete numbers for n, say the number of flips. Let's let m be the number of tails. And maybe we'll consider n and m are 1, for instance. So just take a minute, and if you have some scrap paper or something like that, think about this problem. Think about specifying your observation model, writing down your likelihoods, and maximizing it with respect to this parameter that we want to learn in order to determine the bias of this coin that we're flipping. Okay, so we just have a bunch of binary outcomes, a bunch of Bernoulli variables. So our likelihood is just going to be, assuming that these are IID flips, is going to be lambda to the yi times 1 minus lambda to the 1 minus yi, taking the product over the number of flips that we do, and yi can take 1 if y is tails, 0 if y is heads. If we just care about the likelihood of getting m tails in n flips, and we don't care about ordering, etc., then we just have a binomial distribution as our likelihood. Again, n flips, m observed tails, lambda is the probability of getting tails. We can maximize this fairly easily with respect to lambda. So we could take logs of this expression, for instance, and take derivatives and set them equal to 0 and confirm that we have an optimum and show that the maximum likelihood solution is m over n, where m is the number of tails and n is the number of total flips. So I'd like to ask whether you believe this solution, and I believe a poll is set up. And if you do believe it, why do you believe it? If you don't believe it, why don't you believe it? might be helpful to substitute in some concrete numbers for m and n. So if we imagine that we've just done a single flip and we observe tails, so m is 1 and n is 1, then we're predicting that there's a 100% chance the next flip is tails, which, of course, is not in line with our beliefs. It's basically no information. And so if we arrive at a prediction that we clearly don't believe, then it's probably because our modeling procedure is not honestly representing our beliefs, and we can do something better. So let's consider how to follow a Bayesian approach here. We could choose a prior, which has a functional form lambda to the alpha times 1 minus lambda to the beta. And if we do that, then the posterior will have the same functional form as the prior. This is called a conjugate prior. The beta distribution has this functional form. The gamma functions here are just for normalization, and we can analytically compute the moments of the beta distribution. Here we have visualizations of the beta prior corresponding to different settings of its parameters. We could use it as a uniform prior if we want, so we could just reflect the belief, I don't know what the bias of the coin is. And that'll, as we'll see, potentially give us quite a different answer than just doing maximum likelihood optimization. We could also represent our prior saying, for example, we think that there's probably close to a 50% bias such that it's an unbiased coin, but we're not, maybe it's not quite 50%. Whatever is an honest reflection of our beliefs. And there's quite a bit of flexibility with the beta distribution here. And so applying Bayes' theorem, we can find our posterior, which will be beta distributed with parameters m plus a and minus m plus b. And so we can actually view a and b, the parameters of the beta, as pseudo observations of the flips. And here we have our predictor, the posterior expectation over this parameter, m plus a over n plus a plus b. And I'd like to consider 3 different questions here. 1, what is the probability that the next flip is tails? 2, what happens in the limits of a and b? And 3, what happens in the limit of infinite data? So we can see that if we set m equals 1, n equals 1, and we have a uniform prior setting a equals 1, b equals 1, then we're not predicting that there's a 100% chance that the next flip is tails. And so that's very important already. It's nice as a sanity check to consider limits of different settings of these prior parameters. And so if, for example, a and b are very large, we see that the prior will dominate in our estimator. If we have a lot of data points, if n is very large, then m and n will be large compared to a and b, and we'll eventually recover the maximum likelihood solution, which is exactly what we want. As we get more and more data, eventually the posterior will just collapse onto the maximum likelihood solution. And we can discuss why that happens in more detail later. And I'd like to also have you very carefully consider this last question. It's quite crucial. So does the map estimate that we get by maximizing the log posterior with respect to lambda, which compartmentalizes into the log likelihood plus the log prior, with a uniform prior over lambda, give the same answer as Bayesian marginalization to find the probability that we're going to get tails on the next flip, given what we've observed so far with a uniform prior? So let's take a poll, 1 for yes, 2 for no. Okay, at least one person answered no, which is good. Yeah, so we get a very different answer, as we've seen, when we substitute m and n as 1 and say a and b is 1, giving us uniform prior. And this is a really crucial distinction. We should absolutely not think of Bayesian methods as regularized optimization. Priors are not regularizers. It's a fundamentally different mechanism for reaching our predictions. Even if we say that we don't know what bias we have a priori, it's just uniform for any value between 0 and 1, we're going to be averaging over all sorts of different solutions to get a different answer than if we did optimization. And in this case, with optimization, we can see that that prior would have no effect. It would just give us the maximum likelihood solution because it wouldn't depend on lambda. And so if you don't get anything else out of the tutorial, really understand this point. Bayesian methods are not regularized optimization. And the fundamental difference here is that we're not doing optimization, we're doing marginalization, a posterior weighted model average over different types of solutions. We'll consider one more example and then we'll go to break. So we'll go to break in about 5 minutes. So suppose we have observations y1 up to yn from an unknown density, p of y, and we want to estimate what that density could be. We'll start by specifying an observation model. For example, we could assume that the points are drawn from a mixture of two Gaussians, and our goal is to estimate the parameters of those Gaussians. The parameters in this case would be the means and the variances of the different components and the weights. We can use that observation model to create a likelihood, and then we can maximize that likelihood with respect to our parameters, the mu's and the sigmas. And let's just forget about the w's for now. So I'd like to ask you whether you can just look at this equation without taking derivatives or anything like that and see a setting of parameters which will provide very good likelihood. So if we set the mean, for instance, of the first component, mu1 equal to one of the data points y1, for that term in the product, the x will just disappear. We just get 1 for that, and we get this normalization constant, 1 over the square root of 2 pi sigma 1 squared. We could make sigma 1 very small, and then that term would blow up to infinity. And this other term would still be assigning density to all the different points, so we wouldn't be multiplying against zeros. And we've got infinite likelihood with a solution that we clearly don't believe. I was going to ask you if you believe it, but at the same time, we can probably assume you don't. We don't typically believe that our data are generated from point masses. And when we reach an unbelievable answer, it's typically because we haven't honestly represented our beliefs in the modeling procedure. We could introduce a regularizer, which would go to 0 faster than the likelihood goes to infinity for that pathological setting of parameters. But this could be a little bit ad hoc, and in a sense, we might be okay with including the point mass solution if it's one of an uncountably infinite number of solutions. And in fact, we can use very highly flexible models, even with an infinite mixture of Gaussians, following a Bayesian approach corresponding to Dirichlet process mixture models, which provide very good generalization, even with a small number of points, by doing this Bayesian model average. So to summarize, ultimately, we're often trying to compute this predictive distribution corresponding to our Bayesian model average. And in deep learning, the posterior is going to typically be quite diffuse, meaning that it assigns a fair bit of mass to quite a variety of different solutions, and those solutions are often providing complementary explanations to the problem, such that a Bayesian model average will give you quite a big difference, maybe relative to other model classes. Quite often, in practice, to estimate this integral, which isn't analytic, one uses what's called a simple Monte Carlo approximation, where we take samples from some approximate posterior, either found through deterministic methods like variational Bayes, where we introduce some convenience approximate posterior, like a Gaussian distribution, and we then estimate its parameters to minimize the distance between the true posterior and the approximate posterior, like the KL divergence. For a variational approach, we could see classical training as actually a special case of this. There's also the Laplace approximation, which we'll discuss later, expectation propagation, and many other approaches. Once we've got that approximate posterior, we'll take samples from it in this simple Monte Carlo procedure and that will give us our approximate predictive distribution. We could also get approximate but asymptotically exact examples from a Markov chain Monte Carlo procedure, such as Metropolis Hastings, which is quite popular, Hamiltonian Monte Carlo, which includes gradient information, and was pursued quite successfully by Radford Neal in the mid-90s with Bayesian neural nets, and stochastic gradient MCMC methods, which are up and coming and quite exciting because they algorithmically resemble SGD in a lot of ways, which means they can be applied wherever we apply SGD, often with better results. And we'll be discussing those a little bit later on as well. And we'll also discuss later how we might want to avoid the simple Monte Carlo perspective in some cases. If we're told we can just query our predictive distribution at a small number of locations, which is really the honest truth in Bayesian deep learning. These architectures are massive with tens of millions of parameters at least in many cases, and so it's very expensive to do forward passes and store these models. Where would we want to best query our predictive distribution to get the best possible approximation of this integral? And the answer would rarely be, say, well, take a few exact posterior samples, because they could be redundant. This just would not be a good strategy. So if we attack this instead as an integration problem, we can often get much better answers. And we'll discuss how deep ensembles is actually heuristic for doing that, and we'll consider other approaches as well, which build on that connection for better marginalization. So that's the end of part 1. Shortly, in about 5 minutes, we'll start part 2, where we consider a function space perspective. Thank you. also have an opportunity for some questions at the end of part 2, and I'll try to answer them online. I think we're restarting the live stream as well. So let me just share the screen. All right, you can hear the screen or see, see the screen? Okay, one moment. Great. Okay, we're good to go then. So in this part, we'll be talking about a function space perspective. We've already briefly alluded to this perspective in understanding this model selection question in thinking about support and inductive biases, and we'll go a lot more deeply in this direction, particularly considering GPs, infinite neural nets, what happens when we really pursue this philosophy to its extreme and build neural nets as large as possible. And we'll also consider connections between Gaussian processes and deep learning from the perspective of wanting to perform representation learning and kernel learning. And we'll build on those connections for an approach called functional kernel learning, which really pushes the function space perspective quite far towards trying to do representation learning. And then we'll consider Bayesian nonparametric approaches for deep learning. So the parameters in isolation are completely divorced from the statistical properties of a model. For example, when we were considering that statistics from scratch example, we said that whether or not we want large weights or small weights would entirely depend on the functional form of the model that we're using, its parameterization. Yet, in practice, we often focus almost all of our efforts thinking about these nuisance parameters and trying to learn these parameters and reasoning about these parameters when really all we care about is how those parameters combine with the functional form of a model, f of xw, to induce a distribution over functions. So ideally, we just would like to perform inference directly in function space and in a sense, cut out the sort of go-between that we have with these parameters and think about exactly what we're interested in modeling. And so let's return to this example again briefly, where we have a distribution over linear functions induced by a distribution over parameters, W0 and W1. Here, if we sample different settings of W0 and W1, we get different straight lines with different slopes and intercepts. We can visualize this induced distribution over parameters. We could also consider a much more general model class where we have an inner product of a vector of parameters W with a vector of basis functions. So if we wanted to consider a polynomial basis, the entries of this vector of basis functions phi would be 1x, x squared, x cubed, and so on. We could also have a Fourier basis. This is a fairly general model class, and we'll put a standard normal or a multivariate Gaussian distribution over the parameters W with mean 0 for convenience and covariance matrix sigma W. And I'd like to pause for a minute and ask whether you can derive the moments of this induced distribution over functions. So in equation 38, we have the expectation of this random function, which is random because of the randomness from our parameters W. And we also have our covariance function just going to the definition of covariance. So if you have some scratch paper, just take out your writing utensil and see if you can derive expressions for equations 38 and 39 under the model expressed by equations 36 and 37. So the mean function is fairly straightforward here. If we take the expectation of W transpose phi, as we said, all the randomness is coming from W, so we can pull phi out of that expectation. And the expectation of W, just by our definition in equation 41, is 0. And so we just get 0 as our mean function. We can grind through the algebra under the definition of covariance in equation 43 and show that our covariance function, that is the covariance between a pair of random variables given by our random function queried at a pair of arbitrary inputs, xi and xj, these could be times, spatial locations, images, whatever we like, is going to be the inner product of phi of xi with phi of xj under sigma w. So the next question is whether there are any other higher moments. And the answer to that question is no in this case, because we just have a sum of Gaussian random variables given by equation 40, and Gaussians are closed under addition. And so this distribution over functions is in fact entirely encapsulated by its first two moments, its mean function in equation 42 and its covariance function, also known as its kernel function in equation 45. This is an example of a Gaussian process. And in this case, we can actually do inference directly over functions instead of worrying about the parameters. Formally, a Gaussian process is defined as a collection of random variables, any finite number of which have a joint Gaussian distribution. We can use a Gaussian process to define distribution over functions. F of x is distributed as a GP with mean m of x and kernel kx x prime. Means that any collection of function values, f of x1 up to, say, f of xn, has a joint multivariate normal distribution with a mean vector mu and a covariance matrix k given by our mean function, little m, and our covariance kernel, or our covariance function, little k. So on the left panel here, I have sample functions from a Gaussian process prior. To create this figure, I chose a set of input points, x1 up to xn. I then created my multivariate normal distribution, first by creating my mean function, evaluating my, first creating mu, this mu vector, by evaluating my mean function at all of these input points. And in this case, my mean function I just chose to be 0. So that's just this solid blue curve here. And then creating my covariance matrix by evaluating my covariance function, or my kernel, at all possible pairs of those inputs. So I'll get some n by n matrix. And then I just sampled from that multivariate normal distribution, and I got the black dots, which are the random function values. And then I sampled from exactly that same distribution 2 more times, and I got the purple curve and the green curve. And here I've just joined the dots together. The gray shade shows my 95% credible set. 95% of these functions are contained within the shade. In the right panel, we've conditioned on some data denoted by crosses, and we've inferred a posterior over functions. And here I'm sampling from that posterior to get the black, purple, and green curves. The gray shade shows our 95% credible set. And the solid blue curve, in this case, shows our posterior mean function. So the expectation of this posterior distribution over functions given those observations given by the crosses. And this is, for example, what we might want to use for point predictions, and the credible set is something that gives us a sense of uncertainty. Very crucially, the statistical properties of these functions are very tightly controlled by our choice of covariance function, our choice of kernel. The kernel, in a sense, defines the support and inductive biases of our model. To create these figures so far, I've been using what's called the RBF kernel, the radial basis function kernel, also known as the Gaussian kernel or the squared exponential kernel. And it's equal to just a parameter squared, a squared, times the exponential of our negative Euclidean distance, normalized by, or not normalized by, divided by 2L squared, where L is what's called our length scale hyperparameter. And so this covariance function has a very intuitive inductive bias that random function values that are close together in the input space ought to be more correlated than function values that are far away in the input space. For example, airline passenger numbers under this model between 1951 and 1952 will be more correlated than between 1951 and 1961. So this is actually a pretty broadly applicable inductive bias, and the extent of these correlations will be determined by this length scale hyperparameter L. So if L is small, all the function values basically become uncorrelated. If L is large, then they're correlated over long distances. A is an amplitude parameter, so it controls, in a sense, the height of these functions. On average, the L controls the wiggliness of these functions. In the top right panel, we have a visualization of the entries of a covariance matrix constructed from an RBF kernel evaluated at all possible pairs of ordered 1D inputs, where we see this pronounced diagonal band, indeed saying that things that are closer together in the input space in terms of Euclidean distance are more correlated, higher covariance. As we move away, we actually get uncorrelated. So let's actually instantiate some values for these hyperparameters. Let's choose an A naught and an L naught for our amplitude and length scale. And we'll observe some data and look at the prior and posterior over functions. I'd like you to look at these figures and tell me if anything seems strange about these functions. And it could be actually a little bit subtle. So this is one of the polls. Feel free to respond to the polls. Yes, they look strange. 1, 2, no, they look perfect. So to me, they look a little bit too wiggly. They're oscillating pretty quickly. The length scale perhaps was a bit too small. We see the posterior mean sees a data point, and then it kind of shoots down to the prior mean, which is 0 in this case. So maybe we should consider a larger length scale like here. And they'll ask, does anything look strange about these functions? Well, to me, it looks like we overshot it. Like, before the other functions looked a bit too complex, too wiggly. These look too simple in a sense. They're too slowly varying, maybe over smoothing the data. So we can evaluate our marginal likelihoods. We can actually, in the case of regression here, analytically integrate away our Gaussian process and compute our evidence using the sum and product rules here. We have our likelihood times our prior in this case, integrating with respect to our whole Gaussian process function. And again, the marginal likelihood tells us the probability that we would generate a data set if we were to sample from our prior. And we can use the marginal likelihood to consider model selection. So there's actually quite a beautiful discussion of this in Mackay's textbook on information theory. It's also considered in the Rasmussen and Williams book on Gaussian processes for machine learning and some other works. Again, we've got all possible data sets on the horizontal axis. And on the vertical axis, we have the probability that we would generate each of those data sets, this density. And we can imagine if we have a very small length scale, everything's uncorrelated, so we just have white noise. So surely we've got flexibility. We can generate all sorts of different data sets, but everything we generate will be completely different than anything we've generated so far. And so we're just spreading our mass very thinly over these data sets. We're going to have very bad inductive biases. Whereas if we have L very large, as we saw, we almost start getting basically just straight lines again, even though we do actually have support for quite a few data sets. That support is very strongly concentrated around simple solutions. For a given data set, the marginal likelihood will automatically favor a model of appropriate complexity. It'll have this Occam's razor property. And in fact, if we optimize this marginal likelihood with respect to this one parameter, we get the fit in green, which does appear to intuitively have an appropriate level of complexity. And I'm sure if we were to do a poll, which of these three choices would you use, the red curve, the pink curve, or the green curve? Most of us would go with the green curve for fitting this data. So we can see that we automatically sort of favor this nice minimum description length representation of our data and the marginal likelihood. So at the beginning of this part, I started by saying, well, we can consider some familiar weight space models and then derive the corresponding covariance function we might use for a Gaussian process and then deploy this model in function space. And then I said, well, let's just use the RBF kernel and see if we can get some intuitions. Now we'll step back again and actually derive that RBF kernel from first principles. So we'll again consider a model that's an inner product of a vector of weights and basis functions, but here we're just using scalar notation instead of vector notation. So we're just explicitly writing out the sum that corresponds to that inner product. We'll put a Gaussian distribution over the weights as so, and we'll consider radial basis function, radial basis functions for phi. You can sort of see where the RBF kernel is getting its name now, with centers ci, and we have this sort of bandwidth parameter L. Now, just following exactly the same derivation as before, we can write down what our kernel is. In this case, it's just given by equation 55. And we're visualizing this model in function space in this figure up here. And now let's see what happens as we take the limit of the number of basis functions to infinity. And so we'll want these basis functions to be dispersed across the whole real line. So let's make the endpoints log j and minus log j such that when we take j to infinity, we get infinity and minus infinity. We also want them to be densely dispersed. We want the distances between the basis functions to shrink to 0 as we take this limit. Here, if they're uniformly distributed, then the distances will be 2 log j over j, which we see goes to 0 as j goes to infinity. And this expression for the covariance function in equation 57 becomes a Riemann sum, an integral. We could have, for instance, chosen the endpoints to be root j and minus root j. I just wanted to make sure that the distances between the centers would shrink to 0. That wouldn't be the case if we'd chosen j and minus j, for instance. Okay, so we have this integral. We can substitute in our expression for the basis functions and actually analytically evaluate the integral and recover what's proportional to the RBF kernel. So I'd like you to pause for a moment and really absorb this result. It's really quite extraordinary. We've said here that we can use a model with an infinite number of parameters, an infinite number of basis functions, but using a finite amount of computation if we move to this dual representation in function space. This is actually called the kernel trick. And it's really quite extraordinary. I mean, in that first question I asked with the model selection on the airline passenger data set, you might have thought, well, even if we did accept we wanted to use a huge polynomial, if we take this philosophy to its extreme, how are we even going to represent these models in memory if we have like a 10 billionth order polynomial or something? And this essentially gives us the answer. It says, well, we can actually represent these models that have infinitely many parameters in this dual space and also have a lot of flexibility. So a GP with an RBF kernel is a universal approximator, and you can see this. You can see why intuitively from this derivation. If we were basically to shrink down all of these radial basis functions onto point masses, then we've got densely dispersed point masses across the real line that can take any height, so we can approximate essentially any function we want to arbitrary precision. And at the same time, we've seen that these models have very particular inductive biases. They generate functions in the prior that all have fairly particular statistical properties that will enable us to have good generalization, even on problems with a small number of points. So we have to be very careful not to parameter count as a proxy for complexity. And GPs with RBF kernels really give us a nice balance of large support and well-calibrated inductive biases. I'd like to make a brief aside at this point about the mean function of a Gaussian process. So in this talk so far, we've taken the mean function to be 0 for notational convenience. And this is also the case in many texts about Gaussian processes. It really is just for convenience. One can use any deterministic mean function without really changing the modeling procedure. In fact, it's quite standard to subtract off an empirical mean and then just use a 0 mean GP and then add it back on when you make predictions. Part of the reason for this is also because often the kernel is really the key object of interest in the exposition. And in many cases, there are degeneracies between the mean and the covariance function or the kernel, in which case it's therefore preferred to do the modeling in the kernel. For example, the kernel function shows up in this Occam's factor term that we get in the marginal likelihood as a log determinant, which we'll see later, but not the mean function. And so it's often preferable to really carefully consider modeling the kernel function and not necessarily do a lot with the mean function. Although at the same time, a mean function can be a great way of incorporating scientific inductive biases into a model. Sometimes there's this tension between using the physically interpretable parametric model with parameters that have some scientific significance that have been well motivated by theory, etc., or just throwing your data at a black box function approximator. In many cases, this is actually a false choice. In many cases, we can use both. We can use whatever model we would have used otherwise, the scientifically well-motivated parametric approach, as a mean function, for instance, of a Gaussian process, and then have like a non-parametric relaxation around it with the GP, which allows us to accommodate for the fact that no matter how well-motivated that approach is, it'll still be wrong in some sense. There'll still be some misspecification, and we can correct for that, and we can also represent uncertainty. And so really, it's not, there's not a choice between using a Gaussian process and using some kind of alternative. In many cases, you can make that alternative your mean function and see better performance for doing so. Research on Gaussian processes in the machine learning community was instigated in many ways by work that Radford Neal was doing in the mid-90s on Bayesian neural nets, where he was really embracing this philosophy that we should build highly expressive, highly flexible models. And he took that to its limit. He said, well, let's build Bayesian neural nets that have an infinite number of hidden units. And when he took this limit, he actually showed that these models converge to Gaussian processes using a central limit theorem argument. And so we can see, just taking a simple neural net here, where we have our hidden units H, hidden unit weights U, hidden to output weights V, just a single output function f of x, a bias B, with fairly general assumptions. I mean, the U's don't even need to be Gaussian distributed, et cetera. We can use a central limit theorem argument and show that we'll get a Gaussian process. And as before, we can characterize that Gaussian process by its mean and covariance function, which we can derive in equations 65 to 67. And if we make particular design decisions, like we say that our hidden units are described by an error function, for instance, and we choose a Gaussian distribution for U, then we can derive an analytic expression for the kernel that we get in equation 69, sometimes called a neural network kernel. And we can look at what sample functions from a GP are like under that kernel function. We can see that they're qualitatively a bit different than the sample functions we were getting from a GP with an RBF kernel. For instance, they're non-stationary. We can see the behavior in the center here is quite a bit different than the behavior at the edges, whereas RBF kernels and many popular kernels indeed are stationary, meaning they're translation invariant. Although GPs under those kernels are highly flexible and can describe all sorts of different functions, the statistical properties of draws are kind of similar regardless of where you are in the input space. That's not true for this neural network kernel. We see it's non-stationary. So in the mid-90s, neural nets had been an active area of research contiguously for quite some time. And there was growing frustration over a lot of design decisions associated with these models, which activation functions, which hidden units, what optimization procedure, what learning rate schedule, how many hidden layers, how many hidden units, et cetera, and the lack of a principal framework to make these decisions. And since Gaussian processes could describe infinite neural nets, yet had these very simple inference procedures of the same 10 lines of code, you could get the same answer anywhere. They seemed like these maybe very compelling replacements. Like, let's just use these really nice interpretable models with a few design decisions and interpretable hyperparameters like length scale and a lot of flexibility, and forget about neural networks. And David Mackay did support Gaussian process research, but he was also a bit of a contrarian, and he wrote an article in an edited book about neural networks on Gaussian processes, where he has this quote: "How can Gaussian processes possibly replace neural networks? Have we thrown the baby out with the bathwater?" And what he meant was that neural nets, when they were originally proposed, were envisaged as a step towards intelligent agents, which could discover interesting hidden representations in data, whereas Gaussian processes, at least with kernel functions, which were popular at the time, were basically just smoothing devices, even though they had all of these nice statistical properties. And so we asked, have we thrown the baby out with the bathwater in treating GPs as potential replacements for neural nets? The answer to this question is to build more interesting kernel functions which can discover interesting hidden representations of the data. There's nothing that you can do with a neural net that you can't do with a Gaussian process. You just need the right kernel. And so there's an approach called deep kernel learning, which combines the inductive biases of deep architectures with the nonparametric flexibility of Gaussian processes. These two things are really complementary, even though kernel methods and neural nets are often talked about, especially historically, as competing approaches. They're in many ways offering very different types of advantages, which can be naturally combined. Kernel methods can be seen as providing a very elegant way of representing models with an infinite number of parameters using a finite amount of computation through the kernel trick. So they give you an infinite number of basis functions. Whereas neural nets, on the other hand, give you highly adaptive basis functions with inductive biases that are well suited to a broad range of application domains. And so with deep kernel learning, we can get infinitely many highly adaptive basis functions structured by neural architectures, and we can learn the properties of those basis functions through a GP marginal likelihood. So that's a very different objective than how we would normally train a neural network model. And so we can use these deep kernel learning models for representation learning. Here we have the Olivetti faces problem, where we have faces with different orientation angles. It's a regression problem where we want to predict the continuous orientation angle of a new face. And we can see that when we project what the model has learned into 2 dimensions, where each face corresponds to a line segment and the slope of that line segment corresponds to the orientation angle of the face, we can see that the model is discovering a representation for the data such that faces with similar orientation angles are clustered together. So this is really non-Euclidean metric learning. We can also see this when we evaluate the entries of these deep kernel matrices in the left 2 panels, ordering the faces by orientation angles. Here we see a pronounced diagonal band, which shows that the model has learned that faces with similar orientation angles have higher covariance. This is not something that we could learn with classical kernels or covariance functions, which are based more on a notion of Euclidean distance. In the far right panel, we evaluate a learned RBF kernel on this problem, and we can see that its entries are quite diffuse. So from this perspective, in many ways, training a neural network is exactly like learning a kernel. It's learning a non-Euclidean similarity metric for our data instances. And we can capture this with Gaussian processes using the right kernel learning approaches. And one particular advantage of a Gaussian process is the ability to express a principal probabilistic objective for kernel learning, which might otherwise be difficult. So we can learn kernels with millions of parameters using this marginal likelihood objective and avoid procedures like cross-validation, etc. In this example, we have discontinuous data given by a step function. And we've got fits using a GP with an RBF kernel in blue, a GP with a spectral mixture kernel, which we'll describe briefly, in red, and a GP with a deep kernel in green. The shade here in each case shows the 95% credible set. So from the perspective of a GP with an RBF kernel, even though we have a hyper-flexible model, the step function kind of data is such an unlikely draw from that model. If we can estimate noise, it's much easier for the model to say, well, actually, we think that this data is just noise because our inductive biases are so strongly opposed to this data being anything else. And so we'll just have a huge estimate for uncertainty and have a simple mean fit, which is what we see happens here. In red, we see that the spectral mixture kernel is able to provide a better fit, but it's still sort of over smooths. In green, we can see that the deep kernel captures this data quite effectively. And so there's a bit of a false narrative that GPs can really, over smooth data, have trouble with discontinuities and so on. That's not true. It depends on the covariance function that you're using. And with the deep kernel, you can capture sharp discontinuities and get nice predictive distributions. And you also have this sense of distance in the feature space, which is quite important. So there's been some work recently on single model Bayesian neural nets that sort of, in a sense, have these sort of distance measures encoded within them. And this is something that we get through deep kernel learning. And so that's actually very useful for capturing epistemic uncertainty. Here we consider an autonomous driving problem where we're trying to predict lane boundary positions, and we need to make decisions. And so predictive distributions are going to be very important for making decisions. We don't just want to know where a lane boundary is. We need to know the error bars to make a good decision. And so we use Gaussian processes with LSTM structured kernels and find that we get quite accurate point predictions compared to the standard LSTM models, as well as good predictive distributions. There are many other approaches we can use to develop kernels for representation learning. many of which actually don't rely on neural nets. And this is where this idea that deep learning isn't just about neural nets comes into play here. So this will be a bit advanced. Don't worry if you don't follow everything for the next few slides, but could be of interest here. So I mentioned that many popular kernels are stationary, and there's a theorem called Bochner's theorem that relates stationary kernels to what are called spectral densities. They're just Fourier duals of one another. And so that means that we can reduce kernel estimation in many cases to spectral density estimation. Here we've just represented the two arguments of the stationary kernel as tau being x minus x prime, since these kernels are translation invariant. And so that means that if we attack this as a density estimation problem and say, well, mixtures of Gaussians are dense in the set of distributions, so we should be able to approximate any stationary kernel with a mixture of Gaussians in the frequency space, we can derive basically a closed form basis for all stationary covariance functions, and we can then just estimate parameters in this basis, the sigmas, the variances of the Gaussians in the spectral space, and the mu's, the means of the Gaussians in the spectral space, to do that kernel learning. And we can use our marginal likelihood as our objective, for instance, to learn those types of parameters. And so this is called a spectral mixture kernel. And this is just a brief recap of how we would often use such a model. So we might be considering regression, and our observation model is that we have our latent noise-free function given by our Gaussian process, plus, say, additive Gaussian noise, and that noise-free function could have a spectral mixture kernel with some parameters theta that we're trying to learn. So we'll learn that by optimizing the marginal likelihood, which in this case has the form of equation 75. So we have to solve this linear system and compute this log determinant. And once we have those parameters, we could condition on them and make our predictions. Of course, if we wanted to be fully Bayesian, we still ought to marginalize these parameters as well. Okay, so let's return to the airline passenger number example. Here we've just joined the observations together into a curve. And let's consider various different possible fits and whether we believe them to be reasonable or not. So if we have this red curve here, would you think that this is a reasonable description of the data? No, almost certainly not. That's what we get from a GP with an RBF kernel. We see that it's kind of just smoothing this, in this case, quite a lot and reverting to a prior mean. Does this seem like a reasonable fit? I would say probably yes. And that's what we get through a spectral mixture kernel. And so this again shows the importance of representation learning in order to provide a long-range extrapolation. You may have noticed when I first asked this question about the airline passenger example in part 1, I said, consider trying to make predictions far away from the data. And part of the motivation behind phrasing the question in that way was that when we do extrapolation, we really expose the prior assumptions of our model. They become very, very clear. And we also really need to be able to do representation learning in these settings. So we can apply the spectral mixture kernel to a number of other types of extrapolation problems. Here, green is the withheld test data, blue is the training data, shade is our 95% credible set using a GP with a spectral mixture kernel. The other colors are extrapolations provided using GPs with other popular covariance functions or kernels. In the right panel, we're also visualizing the spectral density. So we said that a spectral mixture kernel was derived by using a mixture of Gaussians in frequency space. And so we can compare that to things like the empirical spectrum and the spectrum associated with things like RBF kernels. In this example, we're trying to recover an unknown ground truth kernel. So we have a controlled experiment where we generate data with a ground truth kernel in green. In the left panel, a heavy-tailed kernel. In the right panel, this quasi-periodic kernel. And then we just feed those data points into our marginal likelihood and then learn the parameters of the spectral mixture kernel and draw what we get. And we can see that it provides a pretty good fit in this instance. In red and purple, we see what we get using, respectively, RBF kernel fits and the empirical spectrum, which is related to just the Fourier transform of the data squared. So we can see that it's actually quite noisy. And this is because it doesn't have great inductive biases. It's not, for example, assuming that covariances are probably decreasing with distance, which is, in general, not a bad inductive bias. Here we have an autoregressive data set, which is representative, for example, of natural sounds. And it, in fact, has a covariance function which takes negative values. So The examples we've seen so far of Gaussian processes are continuous. This is a discrete valued Gaussian process, and we can drive its covariance function. And here with the spectral mixture kernel, we can actually capture negative covariances, which is interesting, and something that we think we probably ought to be able to capture in many cases. In many cases, for example, data have long-range negative covariances. A straight line fit would be one example. We also have this sync function pattern where we're basically observing the data in the top left panel and we're trying to fill in the missing part. We actually had a fun paper called The Human Kernel, which literally asks people to do extrapolations on these problems and tries to reverse engineer their kernel in being able to do this pattern recognition problem. We see that the GP, the spectral mixture kernel, can provide a good extrapolation in this case, although the extrapolations from GPs with other kernels aren't necessarily unreasonable there. Okay, so here we have airline passenger numbers. Again, we see the extrapolation again is reasonable. And this is all kind of automatic. The spectral density in this case is also kind of interesting. We can see that there are peaks in the learned spectral mixture spectrum that do correspond with what we get when we take the Fourier transform, but the Fourier transform is pretty noisy. And so this could be a replacement for a lot of these things. All right, so far I've argued that we, in many cases, want to follow a Bayesian approach because marginalization can be quite compelling and a good way of representing what's called epistemic uncertainty. And also that we want to, in general, follow a function space approach to modeling. And so taking this perspective further, we really ought to approach kernel learning from a function space Bayesian perspective, just the way we approach data modeling with GPs from a function space Bayesian perspective. In a sense, it's a bit strange that with GPs, we put all of this effort into deploying this Bayesian nonparametric distribution over functions to model observed data points. But then the most crucial aspect of this model, the kernel, is either very simply specified, yet we believe it probably to be quite complex to be a good description of reality, and doesn't necessarily capture representation of uncertainty and isn't really thought about from the function space. So the idea here with functional kernel learning is just to take this philosophy a step further in the hierarchy of our hierarchical model and say, well, let's also have a function space distribution over kernels. And we can sample prior kernels from this distribution. We observe some data. Then we can infer a posterior distribution over kernels, which should start to contract around something. And when we form our predictive distribution, we can actually marginalize away this whole posterior distribution over kernels. In this case, we'll actually get a non-Gaussian process. And so this is the hierarchical model specification. And the way that we do it in this case is to put basically a transformed Gaussian process over the spectral density and then compute sort of this integral in order to evaluate our kernel function in data space. And we can see here we have draws of prior kernels, and then we have function draws corresponding to each of those kernels in this hierarchical model. And so this is at the top of the hierarchy. We sample these parameters, then we sample this GP, then we transform the GP, then we sample another GP conditioned on the kernel that we got as a sample from that step up in the hierarchy. And the nice thing about this is we can then intuitively control things like our mean function over kernels. Let's say we would have otherwise used an RBF kernel or a spectral mixture kernel or something else. We could say, well, let's just make that the mean function of our distribution over kernels, and that will concentrate our inductive biases in some nice way, but also allow us to do this interesting representation learning. And when we deploy this model on various different problems, we again see this automatic extrapolation. And we can also apply it to large-scale textures, for example, and see that we can extrapolate somewhat these textures, whereas with an RBF kernel, again, we kind of quickly revert to a prior mean. We also can consider multitask regression problems, and this is quite interesting in the context of kernel learning because often different tasks can be viewed as multiple draws from some shared generative procedure, in which case we get a lot of signal for doing fairly ambitious kernel learning. And here we consider precipitation extrapolation in a bunch of different geographic regions where we're really sharing strength across these regions to learn a really flexible distribution over kernels and make quite good predictions as well as have good credible sets. Now, a big challenge in using Gaussian processes historically has been scalability. As you briefly saw in that set of equations where we were thinking about kernel learning, we need to solve a linear system and compute a log determinant over an n by n matrix if we have n data points. Now, a lot of the progress in deep learning has been driven not purely through methodological innovation, but also through embracing advances in hardware and in systems. We have packages like PyTorch, for example, which leverage auto differentiation and GPU acceleration very effectively. With GPyTorch, this fairly big project we have going, we try to find motivation and inspiration from that trajectory in order to really scale Gaussian processes through systems and hardware acceleration. So we build Krylov subspace methods that enable a lot of GPU parallelization, which in turn enables even exact Gaussian processes to run on millions of points in minutes. This is really quite a big step up from exact Gaussian processes on thousands of points, which has historically been a limitation. And we see that when we do that, when we use these exact methods, we see a big benefit to the nonparametric representation corresponding to these kernels that have infinite basis expansions, such that as we increasingly see more data, we are still very significantly improving in accuracy. Whereas most approaches to scaling Gaussian processes essentially turn GPs from a nonparametric model into a parametric model through a low-rank kernel matrix approximation. This would describe random feature expansions, inducing point methods, etc. And that means that these models won't necessarily benefit from large data sets. So for the first time, we can actually see how well exact GPs can do on huge data sets. And it's often representing a fairly significant gap with the approximate procedures. We can also introduce approximations which exploit algebraic structure in models that is basically a manifestation of the inductive biases that we'll need for good generalization. And so one way to do that is through an approach called structured kernel interpolation, where we basically start with a kernel matrix evaluated on a set of points u, sometimes called inducing points or interpolation points. Then we interpolate on that matrix to approximate the cross covariances between our inputs x and our inducing points u. If we did local interpolation, where we're just considering, say, the two closest points to the x that we're trying to consider in U space, then our matrix W will have only 2 non-zero entries per row. It'll be very sparse. And we can choose the points U in conjunction with whatever kernel we're using to create a structured matrix, which will also admit fast matrix multiplies. And then we can combine with these Krylov subspace methods like preconditioned linear conjugate gradients to efficiently solve linear systems. And so this gives us linear time complexity instead of cubic time complexity associated with Cholesky decompositions and log determinants and things like that. And importantly, it also separates additively across the number of inducing points u, m, and the number of training points n. So often we see something like m squared n sort of inference and inducing point methods. Here we have more like n plus m. And so that means we can make m really large and get a very accurate approximation. In fact, the approximation will be exact as we make m sort of go to infinity, and it'll converge pretty quickly for a number of interpolation strategies. Jake Gardner, one of my collaborators on GPyTorch, made this nice visualization of this structured kernel interpolation, also sometimes known as KISS-GP procedure, where we have these sparse matrices. We're considering a vector multiplication. And we basically are looking at the time and storage associated with each step. Now we have a structured matrix, in this case, a Toeplitz matrix times a vector v, which we can compute in m log m time. And then we have this product here. And overall, we've got very scalable inference asymptotically. And so the nice thing about this approach is we can just make m very large very cheaply. And so even though for a given m, maybe the approach wouldn't be as accurate as some competing approaches, without very much computational overhead, we can make m huge such that if we're considering instead accuracy versus runtime trade-offs, this method can be very compelling compared to the standard alternatives. There are a variety of other Gaussian process libraries like GPFlow, in TensorFlow, GPy in Python, PyTorch, which considers Bayesian optimization, A/B testing. This is what we often use if we're trying to do AutoML, hyperparameter tuning, experimental design, and so on. And these packages have different algorithmic foundations and use cases. There's been a lot of work on combining Gaussian processes with neural nets in various ways. So there's, for example, Gaussian process regression networks and deep Gaussian processes, which build hierarchical models replacing neurons in neural nets with GPs. There are many works that have extended Radford-Niel's limits to multi-layer nets and other architectures. This line of work is very connected to neural tangent kernels for infinite neural net limits with promising results. Deep kernel learning, deep GPs, Gaussian process regression networks, and some other approaches are trying to sort of do metric learning in some sense. I think an interesting direction for a lot of these infinite limits corresponding to various kernels, like neural tangent kernels, would be doing some kind of kernel learning. We emphasize that when we're training a neural net, we're basically learning a kernel. And so in many cases, the kernels we get from these limits are fixed. And I think this is actually a very exciting direction for future work, thinking about how to do representation learning, kernel learning, and those kinds of frameworks. Also, as we've been seeing throughout this part of the tutorial, there are many ways to realize Bayesian principles in deep learning, in addition to the standard approach of marginalizing distributions over parameters in irregular neural nets. We've been considering how we can basically do Bayesian nonparametric deep learning through approaches like deep kernel learning. And I think in general, combining the principles of Bayesian nonparametrics, wanting an infinite number of parameters, wanting a huge amount of support, and so on, with deep learning is a really exciting area for future work and is an important part of the basically the activity in the Bayesian deep learning community. All right, that's the end of part 2. Tomorrow we'll have parts 3 and 4 on practical methods for Bayesian deep learning and Bayesian model construction and generalization. Do we have time for questions, or should we break now? Thanks everyone also for attending. It's been great to have you here. Okay, we have 10 minutes for questions. Awesome. Okay. So I'm just looking at the chat, but I may have missed a question. So if I have, don't be shy about posting it again. So there's a question about, is Bayesian model selection of the underlying parametric model still possible if augmented by a non-parametric GP model? So that's a very great question, and there isn't a short answer. So I think one of the reasons people care a lot more about the kernel in general than the mean function is that the kernel shows up in this log determinant term, which has this Occam's razor property, which is very desirable in doing model selection. And it doesn't really, if we are, if we're just looking at the mean function. However, if we put a distribution over the parameters of the mean function, we can still marginalize it and benefit in the same way. It would involve then approximate inference. So if we're doing regression with the Gaussian process, this could be a bit painful, honestly, because I would say one of the huge advantages of Gaussian processes for regression is quite often we can actually do everything in closed form. We can just write down what our data points are, what model we're using, and then just say, okay, well, this is exactly the equation we want to use to make predictions. There's no sense of like training or SGD or anything like this, which is really beautiful and highly practical. I think this has been very important, for example, in procedures like Bayesian optimization, which are very common use cases of Gaussian processes. And so we would lose that if we were being Bayesian over parameters of a mean function in some cases. But that doesn't mean we shouldn't necessarily do it. And I would say that there's been a lot of good progress on marginalizing kernel hyperparameters. in GP models, which also involves approximate inference. So I think the answer to your question is yes, but there are some caveats, and it can take a lot of work. So if you like, you can unmute, I think. There's a question, does it make sense to sample weight posteriors with MCMC if we have a pretty dense network? So I think that dense networks pose computational challenges regardless of whether we're being Bayesian. Initially, a big obstacle to Bayesian deep learning, say 2016, was indeed having to do a marginalization over like a 10, 20 million dimensional parameter space. And certainly it's still a challenge, but we have made very good progress in being able to approximate that integral effectively and get good empirical results relative to classical training in many instances, and in many instances without a lot of overhead. However, I would say one of the biggest advantages of architectures like convolutional neural nets is not just translation equivariance, but also the sparsity pattern that you get in the weights that enables you to build very deep neural networks, which have that hierarchical structure. If we have a fully connected net, we can imagine even having an image with just 1,000 pixels and saying, well, let's just use 1,000 hidden units. And already we've got 1,000,000 parameters to learn and not even a very interesting model. And so I think there is this big obstacle in these, densely connected, sort of fully connected networks that we often computationally can't just build deep, interesting models because that the number of parameters explodes so tremendously as we change the architecture. So I think that doing Bayesian marginalization would similarly sort of have some challenges, especially if you're trying to build big fully connected neural nets. But they wouldn't be unique to Bayesian procedures. As we'll see in part 3, we'll consider a number of procedures that help us significantly reduce the dimensionality of representations corresponding to large modern neural nets in order to more effectively do Bayesian marginalization. And these procedures could equally be applied to fully connected neural nets, which could similarly provide a mechanism for being Bayesian with those types of architectures. Thank you. Concerning GPyTorch, does the framework also scale well for the computation of posterior uncertainties and correlations? That's a great question. Yes is the answer. There are a couple papers detailing various approaches that have been implemented in GPyTorch specifically for those purposes. I guess a few points to make here. So historically, a lot of the focus on GP scalability has been on training time inference. So that's basically reducing this very daunting n-cube complexity associated with solving linear systems and computing log determinants. But after we've solved those linear systems, et cetera, we still have to make predictions with the model. And that's not particularly inexpensive either. It's just inexpensive compared to that n-cubed complexity. So in the last 3 or so years, there has been a pretty active effort on trying to address those additional computational challenges. How do I get predictive variances in faster than n squared, for instance? How do I get fast posterior samples? And so we had an approach a few years ago at ICML called LOVE, which was extending KISS-GP, which I briefly described just recently in this tutorial. And it enables basically constant time uncertainties and also the ability to query your posterior samples in OT time if you're measuring those posteriors at t points. And these methods are very highly accurate. And so this is actually kind of a big component of GPyTorch as well. Some of this functionality needs to be kind of flagged to turn on, but you can get very, very fast predictive uncertainties and posterior samples. And recently, in the last year or so, there have been a number of new approaches as well that have been looking into these kinds of questions. And the various approaches have often different pros and cons. Mm-hmm.
Perfect. So now we have to move towards our postdoc session. Thank you very much, Andrew.
Thank
And
you.
let's continue your session. Looking forward for the next parts.
Great. Yeah. See you all tomorrow. Thanks for coming.
See you. Have a nice day.
You too. Bye-bye.